The morning air inside the Mitsubishi Heavy Industries research facility in Nagoya smelled of machine oil and uncertainty. It was late March, 1945, and the war had already turned against Japan in ways that could not be spoken aloud. Outside, American B-29s droned overhead with increasing frequency, their 4 massive engines producing a sound that shook windows and nerves alike. Inside the concrete workshop, a different kind of confrontation was about to begin. Chief Engineer Takeshi Yamamoto stood before a wooden crate stamped with English letters. United States Army Air Forces. The crate had arrived 3 days earlier through channels he did not fully understand, salvaged from a downed aircraft somewhere in the Philippines. His superiors had ordered him to examine its contents, to find weaknesses, to prove that American engineering was crude and wasteful. He had spent 20 years designing engines for the Imperial Japanese Navy, building power plants that were marvels of efficiency and grace. He believed in his work the way a monk believes in prayer. The crate contained the remains of a Pratt & Whitney R2 800 twin-wasp radial engine. Even damaged, it dominated the room. 14 cylinders arranged in 2 perfect rows, each as large as a sake bottle. The metal was scorched black in places, warped by fire, scarred by combat. Oil had leaked and dried into dark stains that looked like old blood. Yamamoto circled it slowly, his hands clasped behind his back, his face revealing nothing. His assistant, a younger engineer named Hiroshi Tanaka, stood nearby with a clipboard. Tanaka was 24, educated at Tokyo Imperial University, and still possessed the confidence of someone who had never seen his designs fail. He looked at the American engine with visible disdain. "It is heavy," Tanaka said. "Wasteful. Look at the size of those cylinders. They build with muscle, not mind." That the loudest criticisms often preceded the quietest revelations. Around them, other engineers gathered, their faces drawn with fatigue. The factory worked day and night now, trying to keep pace with losses that exceeded production. Every man in that room understood what was at stake. Japan's aircraft engines, the Nakajima Sake that powered the Zero fighter, the Mitsubishi Kasei that drove their bombers, were masterpieces of lightweight design. They produced remarkable power from minimal displacement. They were efficient, refined, beautiful in their simplicity. But they were also fragile. A single bullet through the oil system meant seizure. A crack in the cylinder head meant catastrophic failure. Japanese pilots had learned to treat their engines like porcelain, nursing them through combat, praying they would hold together long enough to return home. Many did not. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where, in the world you are watching from today. The American engine represented something different. Yamamoto could see it even before the crate was fully opened. The construction was not elegant. It was deliberate. Twin oil lines running to each cylinder, duplicate ignition systems, cooling fins so numerous they formed a labyrinth of aluminum. The Americans had not built for beauty. They had built for survival. "Begin the teardown," Yamamoto ordered. His voice was quiet but carried across the workshop. Tools clattered, wrenches turned. The first cowling panel came free with a groan of protesting metal. Hot air escaped, carrying the smell of burnt lubricant and aviation fuel. The interior revealed itself slowly, like a secret being unwillingly shared. Tanaka leaned closer, pointing at carbon scoring along the cylinder walls. "They run it too hot," he said. "No discipline. Barbaric engineering." Others murmured agreement. The Japanese philosophy of engine design emphasized precision over power, refinement over brute force. Every component was hand-fitted, every bearing matched to tolerances measured in fractions of a millimeter. To them, this massive American engine looked like the work of men who did not understand subtlety. Yamamoto removed his glasses and cleaned them slowly. He had seen enough combat reports to know that American bombers returned from missions that should have destroyed them. He had read accounts of engines continuing to run after sustaining damage that would have shattered any Japanese power plant. The evidence suggested something his colleagues were not yet willing to see. The Americans had solved a problem Japan had never acknowledged. They had built engines that forgave failure instead of demanding perfection. The workshop grew quiet as the engineers removed the next layer of components. Beneath the cowling lay a maze of tubes, wires, and mechanical linkages. Every system appeared to have a backup. Twin magnetos for each cylinder bank, parallel fuel lines, redundant oil pumps. It was a philosophy that seemed wasteful until one considered what it meant in combat. One engineer traced a cooling duct with his finger. "Everything is doubled," he said softly, as if they expect it to fail. Yamamoto nodded. "Not expect," he corrected. "Accept. They accept that failure will occur, so they plan for it." The distinction was profound. Japanese engines were designed to operate perfectly or not at all. American engines were designed to operate imperfectly and continue anyway. Outside, the distant rumble of aircraft engines continued, a constant reminder that the war had entered its final phase. Inside the workshop, the men worked in silence, removing bolts, cataloguing parts, photographing each component. The spring sunlight filtered through high windows, illuminating dust motes that danced like ash. Yamamoto stood apart, watching his team work, feeling the weight of understanding settle over him like a heavy coat. He thought of the pilots he had known, young men who had flown his engines into combat and never returned. He wondered how many had died not from enemy fire, but from mechanical failure. How many had nursed damaged engines through the sky, only to watch them seize moments before reaching safety. The American engine sitting before him represented an answer to a question Japan had never asked. What if survival mattered more than perfection? By afternoon, they had removed the first cylinder bank. The connecting rods lay on the workbench like surgical instruments, each one machined to precise specifications despite the engine's rough exterior. Tanaka measured one with calipers, frowning at the reading. "The tolerances are tighter than I expected," he admitted. "Different factories, yet everything fits perfectly." Another engineer examined the valve train, noting the hardened steel components that showed minimal wear despite obvious combat damage. "They use inferior alloys," he had said that morning. Now, he said nothing. The evidence contradicted the narrative they had been taught. The Americans were not crude. They were simply building to a different doctrine. As evening approached, Yamamoto called for the team to stop. They had learned enough for one day. The workshop emptied slowly, engineers filing out into the twilight, their conversations subdued. Yamamoto remained behind, standing alone before the partially disassembled engine. Oil dripped slowly from an open line, each drop hitting the concrete floor with a sound that seemed impossibly loud in the silence. He placed his hand on the cold metal of the crankcase, feeling the residual texture of combat. Somewhere in the Pacific, an American pilot had trusted this machine with his life. That pilot had flown through flak and fighters, had pushed the throttle forward knowing the engine would answer. And it had. Even damaged, even scarred, it had brought him far enough to fight another day. Yamamoto withdrew his hand and walked to the doorway. Outside, the city of Nagoya lay dark under blackout regulations. Somewhere in the distance, air raid sirens began their nightly wail. He listened to them and thought of the engines that powered the bombers causing that sound. 4 engines per aircraft, 18 cylinders each, hundreds of such bombers now operating across the Pacific. The mathematics of it was overwhelming. Japan had built its aircraft industry around the concept of the superior machine. Each engine a work of art, each aircraft a testament to engineering excellence. But excellence, Yamamoto was beginning to understand, had limits. You could not hand-build your way to victory when the enemy could mass-produce reliability. He returned to his office and opened his notebook. By the light of a single lamp, he wrote a single sentence that would haunt him for the rest of his life. "We have been building engines to impress ourselves. They build engines to bring their sons home." The next morning would bring new discoveries. The team would tear deeper into the American engine, finding more redundancies, more evidence of a philosophy that valued endurance over elegance. But that first day had already planted a seed of doubt in Yamamoto's mind, a doubt that would grow into certainty as the investigation continued. Outside his window, dawn was still hours away. The city slept uneasily, and somewhere over the Pacific, more American bombers were already warming their engines for another raid. Each one powered by machines that refused to quit, built by people who understood that wars were not won by the best engines, but by the engines that kept running when everything else failed. The second day began with rain. It fell in grey sheets across Nagoya, drumming against the workshop roof like distant artillery. The engineers arrived, soaked and silent, shaking water from their coats before gathering around the American engine that dominated the center of the room. Overnight, it had transformed from a curiosity into a challenge, a puzzle whose solution might reveal uncomfortable truths. Yamamoto arrived last, carrying a thermos of weak tea. Rationing had made real coffee impossible, but ritual still mattered. He poured a small cup and stood before the engine, studying it as morning light filtered through the rain-streaked windows. Today they would go deeper. Today they would see the heart of American engineering philosophy laid bare. "Remove the remaining cylinders," he ordered. "I want to see the crankcase interior." The team moved with practiced efficiency. Wrenches turned, bolts surrendered. The massive cylinder heads came free one by one, revealing the internal architecture of the engine. What they found defied their expectations so completely that several men stopped working to simply stare. The crankshaft was enormous, forged from a single piece of steel that must have weighed over 400 pounds. But it was not the size that shocked them, it was the condition. Despite obvious fire damage and combat stress, the bearing surfaces showed uniform wear patterns. No scoring, no galling. The lubrication system had kept it alive even under conditions that should have destroyed it. Tanaka traced the oil galleries with a probe, following passages that branched through the crankcase like blood vessels. "There are 3 separate oil feeds to each main bearing," he said, his voice carrying a note of disbelief. "If one clogs, the others maintain pressure." He looked up at Yamamoto. "This is not crude engineering. This is systematic redundancy." Another engineer, an older man named Sato who had worked on aircraft engines since the 1920s, examined the connecting rods. Each one was stamped with a part number and factory code. "These come from different manufacturers," Sato said. "Different states in America, if I read these codes correctly. Yet they are all interchangeable, perfect fits." The implications settled over the room like cold water. Japanese. Production relied on skilled craftsmen, hand-fitting components, in individual workshops. It produced excellent results, but limited quantities. The Americans had industrialized precision itself. They had turned perfection into a process that could be repeated in factories across an entire continent. Yamamoto moved closer, kneeling beside the open crankcase. Inside, he could see the main bearings still in place, bronze shells that gleamed despite the engine's ordeal. He ran his finger along one surface, feeling the microscopically smooth finish. "How many of these engines do you think they can build in a month?" he asked quietly. No one answered immediately. Finally, Tanaka consulted his notes. "Intelligence estimates suggest Wright Aeronautical alone produces several hundred R-series engines monthly. Pratt & Whitney produces similar numbers. There are other manufacturers as well." He paused. "Thousands per month, across all their facilities." Understanding. Japan's entire aviation industry produced perhaps a few hundred engines monthly, each one requiring weeks of hand assembly. The mathematics of industrial war had become impossible to ignore. Quality meant nothing if quantity could overwhelm it through sheer persistence. By midday, they had reached the magneto housings. Yamamoto had expected to find the standard American dual magneto system, but what he discovered went beyond mere duplication. The ignition system was quadruple redundant. 4 separate magnetos, each capable of firing all 14 cylinders independently. 4 separate distributor systems. 4 complete circuits from power source to spark plug. "They built this engine assuming everything would fail," Sato said softly. He held one of the magnetos, turning it over in his hands. The casing was cracked, clearly damaged in combat, yet the internal components showed minimal wear, and they built it strong enough that when things did fail, something else would carry the load. Yamamoto thought of the Sakai engines in the Zero fighters, beautiful machines, producing 1,300 horsepower from 940 cubic inches. They were marvels of efficiency, achieving power-to-weight ratios the Americans could not match. But a single hit to the oil system meant certain death. There was no backup, no forgiveness. Japanese pilots learned to avoid damage entirely because their engines could not survive it. The American philosophy was different. Accept that damage will occur. Build systems that survive it anyway. It was not elegant, but it was effective. In a war of attrition, effectiveness mattered more than elegance. As afternoon shadows lengthened, Tanaka made a discovery that would change the direction of their investigation. He had been examining one of the cylinder assemblies when he noticed something unusual. 3 of the 14 cylinders showed evidence of catastrophic failure. Pistons seized, connecting rods frozen, the kind of damage that should have destroyed any engine immediately. "Yamamoto-san," Tanaka called out, his voice tight with something between excitement and dread. "You need to see this." The team gathered around the damaged cylinders. The evidence was undeniable. These cylinders had failed completely, yet somehow the engine had continued operating. Yamamoto examined each one carefully, his mind working through the engineering implications. "The crankshaft shows no signs of stress fracture," he said slowly, "which means this engine ran with these cylinders dead. The remaining cylinders carried the full load." He looked up at his team. "We need to test this. We need to know if it will run." The suggestion hung in the air like a dare. Running a captured enemy engine was one thing. Running a damaged enemy engine to see if it would survive its own failure was something else entirely. But Yamamoto had to know, had to see with his own eyes whether American engineering could truly deliver on its 61st implicit promise. That night, as the team prepared to leave, Yamamoto remained in the workshop. He sat on a stool beside the engine, smoking a cigarette in the darkness, thinking about the implications of what they had found. Japan had built its war effort on the assumption of qualitative superiority. Better pilots, better aircraft, better engines, but better had limits. Better required resources Japan no longer possessed. Better demanded time for training and maintenance that the pace of war no longer allowed. The Americans had chosen a different path. Good enough, in sufficient quantities, with enough redundancy to survive chaos. It was the industrial application of overwhelming force, not through individual superiority, but through systematic endurance. He stubbed out his cigarette and walked to the window. Outside, the rain had stopped. Stars were beginning to appear through breaks in the clouds. Somewhere beyond that sky, American factories were running day and night, producing engines by the thousands. Each one built to survive what Japanese engines could not tolerate. Each one bringing the war closer to Japan's doorstep. Tomorrow they would reassemble the engine. Tomorrow they would attempt to start it, damaged cylinders and all. And tomorrow, Yamamoto suspected, his understanding of engineering philosophy would be tested in ways he had never anticipated. The question was no longer whether the Americans built good engines. The question was whether Japan had time to learn from them before it was too late. He locked the workshop door and walked out into the night. The streets of Nagoya were quiet under blackout regulations, but in the distance he could hear the faint drone of aircraft engines. American engines, 4 per bomber, 18 cylinders each. Hundreds of such aircraft, now ranging across the Pacific with impunity. The sound had become the soundtrack of Japan's decline, a mechanical reminder that industrial power could not be overcome by individual excellence alone. In his home that night, Yamamoto sat at his desk and added a new entry to his notebook. "We designed engines that demanded perfection from the world. They designed engines that survived the world as it is. This difference may decide the war." The rain returned before dawn, and with it came the third day of their investigation. The day they would attempt the impossible. The morning of the engine test. The workshop filled with people. Word had spread through the facility that Yamamoto's team intended to run a captured American engine. and engineers from other departments arrived to witness it. Some came out of curiosity. Others came to see American engineering exposed as inferior. None of them knew yet what the engine would reveal. The R2800 sat on a steel test stand, reassembled and connected to batteries, fuel lines, and instrumentation. 3 of its 14 cylinders remained frozen, their pistons seized, their connecting rods locked. Under normal circumstances, attempting to start such an engine would be insane. The imbalanced forces would tear the crankshaft apart. But Yamamoto had examined the design carefully, studied the redundant bearing systems, calculated the stress distribution. He believed it might survive. Tanaka stood beside the fuel pump, his hand on the primer control. Sato monitored the electrical connections. Other engineers positioned themselves at safe distances, some behind concrete pillars, others near the exit. The atmosphere carried the tension of an experiment where failure might be spectacular. Yamamoto stood at the control panel, his hand resting on the ignition switch. "Fuel pressure," he called out. "Stable at 4 pounds," Tanaka replied. "Electrical systems. All magnetos showing continuity," Sato confirmed. Yamamoto took a breath. He thought of all the Japanese engines he had designed, all the pilots who had trusted his work. He thought of the American pilot who had flown behind this engine, trusting it in ways Japanese pilots could never trust their machines. He turned the ignition key. The starter motor whined, turning the massive crankshaft. For 3 seconds, nothing happened. Then one cylinder coughed, another fired. The engine shuddered violently, the test stand's mounting bolts groaning under sudden stress. Black smoke belched from the exhaust stacks. Then, impossibly, the engine caught. The sound was uneven, a ragged thrumming that made the floor vibrate. 3 cylinders were dead, but 11 were alive, and they were trying to carry the load. The test stand shook. Instruments danced in their housings. Oil pressure climbed erratically, dropping and surging as the damaged lubrication system struggled to compensate. The Americans had built cooling systems that could handle uneven heat distribution. They had designed bearing systems that could tolerate imbalanced loads. They had created an engine that could survive its own catastrophic failure. Yamamoto watched the tachometer stabilize at 800 revolutions per minute. The engine was running. Not smoothly, not quietly, but running. He let it idle for 5 minutes, while his team recorded data. Cylinder head temperatures on the working cylinders climbed high, compensating for the dead ones. Oil consumption increased dramatically. Vibration levels exceeded anything a Japanese engine could tolerate. Yet the crankshaft held. The bearings survived. The engine refused to die. "Increase throttle to 50%, Yamamoto ordered. Tanaka looked at him as if he had gone mad, but complied. The roar intensified. The entire workshop seemed to shake. Flames licked from the exhaust ports, blue and orange against the concrete walls. The smell of burning oil filled the air. Engineers covered their ears. Some moved farther back. Yamamoto stood motionless, watching the instruments, feeling the vibration through his boots. If you find this story engaging, please take a moment to subscribe. Enable notifications. It helps us continue producing in-depth content like this. The engine ran for 14 minutes at increased power before Yamamoto finally shut it down. The silence that followed was absolute. Even the sound of cooling metal seemed loud as the workshop processed what they had witnessed. Tanaka approached slowly, his face pale. "It should not have worked," he said. "The stresses, the imbalance, it should have destroyed itself." Yamamoto nodded. "Yes. Under our engineering principles, it should have failed immediately. But they did not build this engine under our principles. They built it to survive what we cannot imagine surviving." He walked to the engine, still ticking as it cooled, and placed his hand on the crankcase. The metal was hot enough to sting, but he kept his palm there, feeling the pulse of residual heat. "This is not an engine," he said quietly. "This is a philosophy made manifest. They accept chaos. They plan for failure. They build systems that forgive mistakes." He turned to face his team. "And we. We have been building engines that demand a perfect world that no longer exists. The implications spread through the room like a cold wind. Every engineer present understood what they had seen. American industrial philosophy had produced something qualitatively different from Japanese precision engineering. Not better in any single aspect, perhaps, but superior in the only way that mattered in war. It could endure. Sato broke the silence. How many of these engines do they have? The question had no good answer. Thousands, certainly, perhaps tens of thousands by now, each one capable of surviving damage that would ground any Japanese aircraft. Each one produced by factories that operated at scales Japan could not match. The mathematics of attrition had become clear. That afternoon, as the team began documenting their findings, an air raid siren split the air. American bombers again, heading toward Osaka or perhaps Tokyo. The engineers paused in their work, listening to that distant drone. 4 engines per bomber, 14 to 18 cylinders each, redundant systems throughout, machines built to survive battle damage and keep flying. Yamamoto walked outside and looked up at the contrails, scratching across the blue sky. Somewhere up there, American crews were trusting their lives to engines like the one his team had just tested. Engines that would bring most of them home, even when damaged, even when operating on reduced power, even when everything that could go wrong had gone wrong. Japanese pilots had no such luxury. He returned to the workshop and began writing his report. It would be the most difficult document of his career because it would require admitting truths his superiors did not want to hear. That American engineering was not crude but deliberate. That redundancy was not waste but wisdom. That Japan's philosophy of perfection had become a vulnerability in a war of attrition. As evening approached, Yamamoto stood alone before the American engine one final time. Its cylinders were cold now, its fires extinguished, but the lesson it taught would burn in his mind for the rest of his life. The Americans had not built the best engine. They had built the engine that wars demanded, one that survived chaos instead of requiring order, one that forgave failure instead of punishing it. He thought of the young pilots he had known, brilliant men who had died not in combat but from mechanical failures their perfect engines could not forgive. He thought of the American pilots flying home on engines that should have failed but chose to keep running. The difference between those outcomes was not courage or skill. It was philosophy. Yamamoto closed his notebook and prepared to leave. Tomorrow he would present his findings to the technical committee. He would tell them what they did not want to hear. That Japan had been building engines for the war it wished to fight, while America had built engines for the war that actually existed. Whether anyone would listen was another question. But he had to try. Outside, night was falling over Nagoya. The city prepared for another round of blackouts and air raid alerts. And somewhere over the Pacific, more American bombers were warming their engines, each one powered by machines that had learned to survive what Japanese engineering had never imagined building for. The sound of those engines would grow louder with each passing week until it filled the entire sky. The technical committee met in a windowless conference room 3 days after the engine test. 12 men sat around a polished table, senior engineers and military officials whose faces carried the weight of a war that was slipping beyond control. Yamamoto stood at the head of the table, his report bound in plain covers, his hands steady despite the trembling he felt inside. He had spent 3 nights preparing this presentation, knowing that what he was about to say would challenge every assumption these men held about Japanese technological superiority. The projector clicked on, casting images of the American engine onto the wall. Yamamoto began with facts: displacement, horsepower, weight ratios. The numbers told a story of brute force engineering, machines that prioritized reliability over refinement. Then he showed the photographs of the damaged cylinders. 3 frozen solid, connecting rods seized, pistons locked in place. He described the test in clinical detail. How the engine had started, despite catastrophic damage. How it had run for 14 minutes with nearly a quarter of its cylinders dead. How the redundant systems had compensated automatically, redistributing load without human intervention. The room remained silent as he spoke. Some men took notes. Others simply stared at the images, their faces revealing nothing. When Yamamoto finished, he returned to his seat and waited. The silence stretched. Finally, a colonel from the Army, Air Service, leaned forward. "You are telling us," he said slowly, "that American engines are superior to ours." Yamamoto chose his words carefully. "I am telling you that American engines are designed for different priorities. They sacrifice efficiency for redundancy. They accept higher weight for greater reliability. In a war of attrition, these trade-offs favor survival over performance." Another officer, a Navy captain who oversaw fighter production, shook his head. "Our Zero fighters achieve their range and maneuverability precisely because we minimize weight. If we added American-style redundancy, we would lose our tactical advantages." "Yes," Yamamoto agreed. "That is correct, but we would also lose fewer pilots to mechanical failure. The question is which loss we can afford." The statement hung in the air like an accusation. Everyone in that room knew the statistics. Japanese pilot training took 2 years. American pilot training took less than 1. Japan could not replace its losses. America could. The mathematics of attrition favored systems that brought pilots home, even at the cost of performance. A senior engineer from Nakajima Aircraft spoke up. "Are you suggesting we abandon our entire design philosophy, that we rebuild our industry around American principles?" Yamamoto shook his head. "I am suggesting we understand why their engines survive conditions ours cannot. Whether we can adapt those lessons is a question of resources and time, neither of which we have in abundance." The truth of that statement settled over the room like ash. By spring of 1945, Japan's industrial capacity was collapsing under sustained bombing. Raw materials were scarce, skilled workers had been drafted, factories operated at fractions of their capacity. Even if Japanese engineers wanted to rebuild their engines around redundancy principles, the infrastructure to do so no longer existed. The meeting concluded without resolution. The committee thanked Yamamoto for his thorough investigation and assured him his findings would be considered. He knew what that meant. The report would be filed, classified, and forgotten. Japan would continue building the engines it knew how to build, even as those engines failed with increasing frequency. There was no alternative. Walking back to his office through spring rain, Yamamoto felt the weight of futility. He had documented the truth, but truth could not alter the trajectory of a war already decided by industrial mathematics. American factories were producing engines at rates Japan could not match. Each one built to survive battle damage Japanese engines could not tolerate. That evening, he received word that Tanaka had been drafted. The young engineer who had worked beside him throughout the investigation would be sent for pilot training. Yamamoto tried to imagine Tanaka flying a Zero powered by a Sakai engine, trusting his life to a machine that could not forgive a single bullet through its oil system. The image was too painful to hold. Weeks passed. The bombing intensified. Nagoya was hit repeatedly, B-29s flying in formations that darkened the sky. Yamamoto listened to those engines from the shelter beneath his factory, hearing in their steady drone the sound of systematic industrial power. 4 engines per bomber, redundant systems throughout, machines built to complete their missions even when damaged. The Mitsubishi facility took hits in late April, 3 workshops destroyed, including the one where they had tested the American engine. Yamamoto learned later that the engine itself had survived, pulled from the rubble by salvage crews. It sat now in a storage yard, scorched by fire for the second time, yet somehow still intact. Even in death, it refused to be destroyed completely. By June, the situation had become desperate. Japan's oil reserves were nearly exhausted. Aircraft production had fallen to a fraction of wartime peaks. The remaining fighters flew with partially trained pilots in engines that had been overhauled so many times they barely held together. Yamamoto spent his days trying to keep production lines running, improvising repairs with whatever materials remained. One afternoon, he found Sato in the workshop, disassembling a Sakai engine that had failed after only 12 hours of flight time. The crankshaft had cracked, a failure mode that should have been impossible with proper maintenance. But proper maintenance required oil that no longer existed in sufficient quantities. "We are building engines for a war that ended months ago," Sato said quietly. "We just have not admitted it yet." Yamamoto said nothing. There was nothing to say. The American engine had taught him that industrial war rewarded different virtues than individual excellence: redundancy over refinement, reliability over performance, survival over perfection. Japan had optimized for the wrong variables, and no amount of engineering, brilliance could compensate for that fundamental error. In July, as American bombers ranged across Japan with virtual impunity, Yamamoto was ordered to write a technical manual on engine maintenance under resource-constrained conditions. It was an impossible task, like writing instructions for breathing underwater. But he tried. He documented every improvisation, every shortcut, every technique for extending engine life beyond designed limits. The manual would never be widely distributed. By August, the war was effectively over. Hiroshima, Nagasaki. The Emperor's radio address. Yamamoto heard the announcement in his office, the static-filled voice telling the nation that the war had ended in ways that did not mention defeat. He sat in silence for a long time afterward, thinking of all the pilots who had died trusting engines that could not save them. That night, he walked through the damaged factory one final time, past the silent assembly lines, past the cold furnaces, past the workshop where they had tested the American engine months earlier. The building was a shell now, roof partially collapsed, walls scarred by fire. But in the rubble, he found what he was looking for. A small brass plate that had been attached to the American engine, Pratt & Whitney, Hartford, Connecticut. He pocketed the plate and walked home through streets filled with silent crowds. The war was over, but its lessons would haunt him for years to come. He had seen the future of industrial engineering in that American engine, had watched it run on 11 cylinders when it should have died. He had documented the philosophy that created it: redundancy, reliability, survival. But documentation could not change the past. The years after the war were difficult for Yamamoto. He found work with a civilian manufacturing company, designing engines for trucks and generators. The principles were similar, but the stakes were different. No one died when a truck engine failed. He could design for efficiency again, without calculating the cost in lives. But the memory of that American engine never left him. In 1948, he received a letter from the United States. It came from a former Army Air Forces engineer named Robert Preston, who had read a translated excerpt of Yamamoto's technical report through occupation authorities. Preston wrote that he had worked on R-series radial engines during the war and was impressed by the thoroughness of Yamamoto's analysis. The letter included a photograph. Preston standing beside a B-29 at an air show in California, one hand resting on the cowling of an R2800 engine, the same model Yamamoto had tested. Preston had written on the back, "These engines brought me home 37 times. I trusted them with my life." Yamamoto kept the photograph on his desk. Sometimes, when design problems seemed impossible, he would look at it and remember the sound of that engine running on 11 cylinders. The lesson it had taught him about engineering philosophy. That survival was not a compromise but a virtue. That redundancy was not waste but wisdom. That the best design was not the most elegant, but the one that kept people alive. In 1952, Yamamoto was invited to speak at a technical conference in Tokyo. The subject was post-war aviation development, but his speech became something else. He spoke about the American engine, about testing it in 1945, about watching it run with catastrophic damage, about understanding too late that Japan had optimized for the wrong variables. "We built engines that demanded perfection," he told the audience. "They built engines that survived imperfection. In war, survival matters more than beauty. In life, perhaps it matters more than anything." The speech was controversial. Some attendees criticized him for praising enemy engineering. Others understood what he was trying to say. That engineering was not about national pride or aesthetic perfection. It was about solving problems in ways that served human needs, and sometimes the best solution was not the most elegant, but the most forgiving. Yamamoto retired in 1961. He spent his final years in a small house outside Nagoya, tending a garden and writing technical memoirs that few people read. He never published the full story of testing the American engine. Some experiences were too personal to share, but he kept his notebooks, filled with measurements and observations and reflections on engineering philosophy. In 1968, he received another letter from Preston. The American engineer was retiring and cleaning out his office. He had found an old photograph from the war years, workers at the Pratt & Whitney factory in Connecticut assembling R-series engines. He thought Yamamoto might find it interesting. The photograph showed dozens of people, men and women in work clothes, bent over engine components on assembly lines. Their faces were not visible, but their posture suggested concentration and purpose. Preston had written on the back, "These people never flew, but they built the wings that carried us." Yamamoto studied that photograph for a long time. He thought of his own team. Tanaka, who had been killed in pilot training in 1945. Sato, who had survived the war but died in a factory accident in 1950. All the engineers who had worked beside him, trying to keep production running as the war collapsed around them. They had built engines too, beautiful engines that reflected Japanese precision and craftsmanship, but they had built for the wrong war. The American workers in Preston's photograph had built for the war that actually existed, chaotic, brutal, unforgiving. They had built engines that survived chaos instead of requiring order, and in doing so, they had helped win. Yamamoto died in 1973. His funeral was small, attended by former colleagues and a few family members. Among his effects, his children found the brass plate from the Pratt & Whitney engine. They did not understand its significance and nearly discarded it. But Yamamoto's eldest son, an engineer himself, recognized the care with which his father had preserved it. He kept it, mounting it in a small frame with a note his father had written. "This plate came from an engine that taught me humility. It showed me that the best engineering serves life, not pride. Remember this when you design. Build for survival, not perfection." The note hung in the son's office for 30 years. Eventually, it was donated to a technical museum in Tokyo, where it remains today alongside other artifacts from Japan's aviation history. Few visitors understand its significance. It is simply a brass plate from an American engine, scarred by fire, carrying a name most people do not recognize. But for those who know the story, it represents something profound. The moment one engineer understood that his entire philosophy had been wrong, that perfection was not the highest virtue in engineering, that survival was, that the machines which brought people home mattered more than the machines which impressed other engineers. The American workers who built that engine never knew a Japanese engineer tested it and learned from it. They never knew their redundant systems and fail-safes would teach lessons that outlasted the war. They simply built what they were told to build, trusting that somewhere, somehow, it would make a difference. And it did. Not just in winning a war, but in changing how one man thought about engineering, how he taught his students, how he approached every design problem for the rest of his life. The lesson was simple but profound. Build for the world as it is, not as you wish it to be. Accept that failure will occur. Plan for it. Design systems that survive it. Value endurance over elegance. Choose reliability over refinement. This was not a surrender of excellence. It was a redefinition of what excellence meant. Not the machine that performed perfectly in ideal conditions, but the machine that continued functioning when everything went wrong. Today, modern aircraft engines reflect these principles. Redundant systems throughout, fail-safes at every critical point, designs that tolerate damage and continue operating. The philosophy that American engineers developed during World War II has become standard across global aviation. not because it produced the most beautiful engines, but because it produced the engines that kept people alive. Yamamoto would have recognized this evolution, would have seen in it the vindication of the lesson he learned testing that damaged American engine in 1945. That engineering was ultimately about serving human needs, not satisfying aesthetic principles, that the best design was the one that brought people home. In a quiet corner of that Tokyo museum, the brass plate still hangs, Pratt & Whitney, Hartford, Connecticut. Beside it, a small placard explains its history, how it was salvaged from a captured American engine, how a Japanese engineer tested that engine and learned from it, how that lesson changed his understanding of what engineering should be. Few visitors stop to read the placard. Most walk past, drawn to more dramatic exhibits, fighter planes, bombers, the machinery of war displayed in frozen poses. But sometimes an engineering student will pause. We'll read about Yamamoto and his test. We'll understand that the greatest technical achievements are not always the most visible, that sometimes the most important lesson is learning what you were wrong about. That humility can be a form of brilliance. The engine that taught Yamamoto that lesson is long gone, destroyed in salvage operations after the war, but its influence remains. In every redundant system, in every fail-safe mechanism, in every design choice that values survival over perfection, the Americans who built it never intended to teach their enemies. They simply built the best engines they could for the war they faced. And in doing so, they created something that transcended victory, a philosophy of engineering that served life itself. Yamamoto understood this in the end, not during the war, when pride and necessity blinded clear thinking, but afterward, when reflection became possible. He understood that the sound of that engine running on 11 cylinders was not the sound of American superiority. It was the sound of engineering serving its highest purpose, keeping people alive despite impossible odds, building systems that refused to abandon those who trusted them. This was the lesson that outlasted the war, that survived in notebooks and memories and brass plates preserved in museums, that influenced how engineers thought about design for generations afterward, not through lectures or textbooks, but through the simple story of one man testing an enemy's engine and discovering that his enemies had understood something he had missed. That survival was not a compromise, it was the goal. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.